Okay, recording is now. Thank you, Oscar, the Spanish president of the IEEE, the Spanish chapter of the Education Society. Oscar, you can introduce the webinar.
Thank you, Manuel. Welcome to everyone one day more to this series of the webinars about Internet of Things and education. And I want to thank also to the rest of the sponsor, the Portuguese chapter and the Bangalore chapter and the other sponsor, and especially to the speaker of today, Alejandro Macho. Welcome. The title of the webinar is FPAAs, Education and Remote Laboratories. Hope you will enjoy, and thank you very much to all the attendants for this webinar. Thank you.
Thank you, Oscar. Would you like to say something in the introduction, Pedro, as the chapter chair of the Portuguese chapter of the IEEE Education Society?
Hello, I'd like to welcome everyone and thank Alessandro Macho for being available for this presentation. And as I said before, it's an honor for us to contribute for this organization.
And thank you. And one of the other sponsors of the webinars are the Spanish Association of the Education Engineering, the CEPI. This is another sponsor too for the webinars. And finally, Siva, you'd like to introduce Alex and of course introduce the Bangalore chapter.
Good evening. At the outset, I would like to welcome Pedro Fonseca from Portugal. It's a pleasure to meet you, sir, on this occasion. Otherwise, it would have been difficult for us to meet face to face. The pandemic has given us a lot of advantages and disadvantages. So yes, both are there, but let us take the advantages and forget disadvantages. Yeah, today's topic is quite an interesting topic. An emerging area, field programmable analog arrays. We would like to know something about this. And at this juncture, I would like to tell IEEE Bangalore section is the largest section in India. We have 10,000 IEEE members. We have crossed 10,000 just on 21st of this month. We crossed 10,000 membership, and we stand we are the second largest in the region 10. As far as the membership is concerned, it's a very vibrant community, IEEE Bangalore section, and so we have quite a good number of chapters, very vibrant chapters. IEEE Education Society is a new chapter, whereas all the others are quite old chapters who they have their presence for last 15 years, 20 years, like that. So I would like to introduce today's speaker, Alejandro Macho. He has obtained his MSc degree in Electrical, Electronics and Control Engineering from the Spanish University for Distance Education, Madrid, 2016, and BSc in Industrial Electronics and Control Engineering from the University of Castilla. And in 2014, he is an IEEE member since 2011. He has worked in Deloitte since 2014 as a senior technology consultant and collaborated with the innovation team. Furthermore, he was the president of the National Association Cubic, an association for students, professors, and educational institutions who pursued a great impact and innovation in education. He has been the vice president for the Foro Estudios Unidas Hispana from 2011 to 2016, and he has collaborated with companies like Microsoft. Alejandro is a PhD candidate at UNED IEEC department. With this brief introduction, I would like to welcome Alejandro Macho for this special talk on FPAA, education and remote laboratories.
Perfect, thanks. Then we can start.
Great, thank you for giving me the opportunity to be here today, and thank you all for connecting and for registering to this event. As they have said, we are going to talk about FPAAs and its use in education and of course in remote laboratories. So the index for today, I'm going to be speaking for around 30 minutes, I hope, more or less, or more. We are going to talk about FPAA, what they are, because some of you may know this device, but some of you don't. So we are going to talk about this. It is kind of known because of being the analog hosting of the FPGAs, but they are less developed. They are less known. So we are going to talk about a little bit about them and about the most important features and characteristics. Then we are going to talk about how to program those FPAA, not only because of our point of view as facilitators or professor, but also from the point of view for the student, because I think it's so important too. Then we are going to talk about dynamic reconfiguration. This is like the key thing that let us do some things that improve its performance in education and in remote laboratories. At the end, we will talk about some examples and some application we have developed for the use of the FPAA in education, and also for remote laboratories. We're going to talk about some ideas in order to use those characteristics in this scenario. So, talking about the FPAAs, they are programmable analog devices, and they are not new. That term was first used in 1991. I wasn't born yet, so they are not that new. They have been in the market for the last 20 and a lot years, and they work like different functional blocks that performs different tasks or functions, and once you interconnect all of them, you have the final application. And that is important because inside of those FPAA, there are like two main groups: the one that works in a continuous time and the one that works in discrete time with different techniques. We have worked with the discrete times and with it, and they are manufactured with the technique of switch capacitors, and that is important too because it let us to emulate the resistance behavior with a capacitor and switching switch capacitor technique. It let us to build a device like the FPAA, which is very small, and we can change in its behavior very quickly, and it makes possible also the dynamic reconfiguration. So this feature is very important, and this characteristic is one of its main ones. It is also good to speak about the main manufacturer. It is Anadin, because as the FPAAs, there are big players, but Anadin is the big one here. So if you want to know anything about the FPAAs, or you want to download some datasets or whatever, just type Anadin at Google and you will find all of them. It is important to the concept of CAP, because CAB, because these FPAA are organized in CAPs. Those CAPs are different units with different resources. So you are going to consume all those resources in order to build your application, and you have to keep that on mind in order to build your final application, because you need to select what resources are being used in each CAP, and you cannot route different resources at different CAPs. So that's a limitation in general. But well, the software development environment and so on will give us some opportunities to make this process easier for us. Anyway, as I told you, we're working with an FPAA that works in a discrete time, and this is the one we have been using. This is not the most recent one, but it's very similar to the most recent one. The good thing is that they are pretty cheap. They are pretty easy to use, and as you can see here, there are some different components, but we are going to talk about the most important ones. First of all, the CAPs. As I told you, this one has 4 CAPs with different resources, and all of them has access to the lookup table. And this is important because some components work with access to this lookup table, so we don't need to take into account in which CAP we are using those components, because all of them have access to the lookup table. But maybe the most important thing here is the SOBRE registry. those registries store the next configuration byte stream, and that is very important because while configuration run holds the current configuration, the side run can store the next configuration while we are transmitting it. So we don't need to stop the device to work, and we can reconfigure it on the fly. And here a very important limitation, it is like, as I told you before, FPAA are not as developed as FPAA. So we don't have yet, we don't have like critical devices, I mean, for critical applications. So we cannot talk about real reconfiguration on the fly, but for purposes in education, it is like a reconfiguration on the fly. We are not going to notice any delay, any reset, but I wouldn't use this for critical application, for example, in transport or whatever. But the concept is here, I think, is that is the thing that is important for us today. So I just wanted to make this disclaimer. So Salron is going to be the key thing that let us do the dynamic reconfiguration. We are using Anadin development board AN221 key 04 version 3, and there is a newer version, so you can check that on the website. Here, there is another important thing. With those development boards, we can work in the daisy chain mode, and that is important because of two things. Since they are not very developed, as I already told you, we are going to have limited resources, but we can use different boards, so we will have more resources available. But the most important thing here is we are going to be able to control all of them with one just control unit, a computer, for example. So in the case of remote laboratories, we are going to have one control unit controlling different FPAAs that can be different labs, different modules, whatever. And that is one advantage of these boards. So having spoken about the FPAA, now we have to talk about how to program them. And in this case, it's very, very easy because we have like a visual tool to do that, and it is for free. You can download it from the Anadin website, and it's called Anadin Designer 2. So in this case, you will have to drag and drop some elements, and those elements are called CAM, Configurable Analog Module. Those can be, for example, a signal generator, or a divider, or a multiplier, or, you know, gain component. So easy to program, to understand. It's easy to simulate, to test that everything is going well. And for the student, it's so easy because they can see what they are doing and they don't need to code anything. The suite also comes with specific tools because the FPAA are like general purpose devices, but they are very good for specific tasks. For example, filter is one of them, and we will have a specific tool to create filters. We are going to be able to select different parameters and to see different features, and the software is going to use all the resources available in the FPAA with the different caps to build this filter. Also, with the control part, we have Anadin PAD, and we are going to be able to create some modules in order to make this control possible, and it will use the available resources in the more efficient way. But also, those are specific tools I wanted you to know, because if you want to show the students or whatever some specific application, those are very good because it lets you create very professional applications very easily, and then you can create them also with the general designer, which is also very good in order to show a student how to use different cams and different blocks. Some example for the cams, so you can have an idea of all of this. This is just an example for this development board. So you have different cams, and the important one good thing here is that we will have all the information available. I mean, we can check, for example, in this low corner, in this filter linear, we can see what are the limits for the current frequency, for the gain, how it is built with the switch capacitor technique. So it is useful not only for its use, but also for in order to know how it's built. So it will depend if we are in engineering, higher education or not, if this information is going to be useful. But for us as facilitator or teachers, I think this is going to be very, very useful to us. And of course, when we are going to use one of these cams, in order to configure them, it's going to be so easy, because we only need to select what we want to use. In this case, for example, we can select the filter type between low pass, high pass, off pass, 410, whatever. Phase 1 or phase 2 it is because we are working in discrete time. So clocks are important. We are working in different phases. So we are not working in the real continuous time, but and I'm not going to enter on the details, but the different cams can work only in phase 2 or only in phase 1, and we can select it to polarity, inverting or not inverting, and of course the corner frequency and the gain. So it's so easy to create the application, and we can understand what we are doing. We don't need to handle the physical resources of the cap of the FPAA. So it's so easy for us, and it will be so easy for students. And of course, since we are working with clocks, and that is not so easy to understand, sometimes the software environment is going to help us with some messages, not only telling us what we can do or what we cannot do, but also explaining to us some limitations depending on the cam we are using. So well, this is like a final design. So it looks like that. We have the inputs, we have the outputs, and then we have the different blocks that they are going to perform some things. And it is very easy to simulate because we have just the functionality on the application, and we can create the inputs, and then we can check different measures in order to have the simulation done. So it's like very, very easy to use, very few functionalities, but really useful. So we can test everything without the need of having the hardware. So if we are creating lab practices or whatever, and our students need to perform them on the lab, but they can do some work, some previous work from home or whatever, and they can test their designs. In this case, for example, if we are going to, we want to model a signal in amplitude or frequency, and this is like the final design. And once we simulate everything, we are having here the different signals. So it's very easy to use. Any student, any engineering student could use it very easily because they are used to other tools or to other simulators. So that is not the most powerful tool, but powerful enough to accomplish with most of the tasks. And we can simulate different boards. So we can work in daisy chain, we can simulate them, and we are ready to program and to control everything with one single control unit. And this is going to be very important for the remote laboratories application. So having spoken about the FPAA and about how to program them, we're going to talk about the dynamic reconfiguration. This is like the most important thing, and that the characteristic that let us do some very interesting applications in education and for remote laboratories too, of course. So we have two of them, the state-driven method and the algorithmic method. The state-driven method is simpler, and we will need less resources in order to perform it or to control it. And the algorithmic method is more complex, but we will have endless possibilities to do. I'm going to talk about both of them. So first of all, the simpler one, the state-driven method. This is simpler, but it is also very powerful because we only need a very, not a very powerful control unit. For example, we can do it from using a peak, a mid-range peak. But the thing here is we need to know the different states on the design phase. I mean, for example, we can know, okay, we are going to work in an environment with 5 different situations, or with four situations. This case, for example, is for 5. We have an initial state. Sorry, it is in Spanish, but I think you will understand. So estado inicial is initial state, and that is like the primary configuration, and our device will be working with that configuration, and then we will be able to change from one to another, the configuration 1, the configuration 2, 3, and 4, and we can jump, for example, from 1 to 4 or from 1 to 3, no problem at all. We need to control when we are going to switch from one to another. And for example, in this example, we are changing every 1 second. So we can sense the environment in order to decide. We can do it, for example, from 1 second to another, like this example. And this is so easy because we are going to generate the byte stream of the reconfiguration while we are designing the application. So we need to know, and the final application won't adapt to anything else that hasn't been taken into account on the design phase. Okay, that's the question, but we will have the possibility to implement this reconfiguration with a very simple control unit. Some application with that, for example, if we are going to sense different sensors, we are going to adapt different signals, and we know when this is going to happen. This is so easy to use and so cheap if we talk about resources. The algorithmic method is more powerful. It lets us do like endless possibilities. In this case, and as you can imagine, because it's named, we will have different functions. For example, for the filter, we will have a function, and we can select the corner frequency and the gain. So once we execute this function, we're going to have the bit stream, and we can send it to the FPAA, reconfiguring this device on the fly. We can change the gain or the corner frequency in all their values. We don't need to know the different scenarios or the different situation during the design stage. The only thing we need to know is which cam we are going to use, because the parameters are can be reconfigured on the fly at the time we want to. On the other hand, we will need a full control unit here, for example, a Raspberry Pi or a computer. We have developed some examples using the computer because it is so useful for students if we develop a friendly user interface. We are going to see them right after this. So this is an example of what we can build for computer. For example, we can build an interface with a slide bar in this case, and we can move the slide bar from one place to another, and it will change the parameter. Imagine in this case, it could be the gain. So we can move from one gain to another, and then click the download button, and we will transfer the new configuration. But we can do other things. For example, we could, and we have done that. We can do that, for example, when you move the slide bar, automatically it reconfigures the FPAA. And I have told before that they are not made for critical applications. So sometimes it cannot be like real time, but we are talking about milliseconds. So for example, if we are using a filter and then we are modifying the corner frequency with this slide bar, we can move the slide bar, and in real time we can see on the physical device that everything is changing, and if we are measuring the signal, we are going to see the effects. So this is like so important for a student, because imagine if you want to focus on a concept, for example, in a low pass filter, and you want to focus on how to the different effects that can have a different corner frequency, and the student just need to move cursor from one place to another in the sidebar. It's so easy for them. It's completely safe. Imagine this for students that are not they are not in higher education, but you want them to understand some parameters or some concepts. It's so safe and very easy to use. I'm going to talk about other application in the next example. So I wanted to tell you different use cases for the dynamic reconfiguration and FPAA in education. First of all, in higher education for technical students, I think this is so easy to understand. If we have some applications, some tools, and a device that can be reconfigured on the fly and very quickly, we have the possibility to spend the lab time in a more efficient way. We are going to use the time for the concepts or that we really want to, and we are going to avoid some problems, because sometimes if you need to use discrete components in a breadboard or whatever, sometimes you are getting problems that are not intended to, and you are losing a lot of time until the professor or the facilitator can help you, and you are not using wisely your time. So this is one of them. Also, it is good for universities or colleges, because you can have like different labs, different practices in one single device. So if the cost is important, because sometimes it is, this is a very cost-effective way to have like a very complete lab. Also for early and medium level, this is also, and I really like this one, because you can abstract the concepts, and you can let the student play with the concepts they know, and you can mask everything out. I mean, for example, if you are using a filter and you want the students to interact just with the gain or just with the corner frequency, you can mask everything out, or you can translate that. They are going to interact with the concepts they know, and they are going to be able to play with those concepts without worrying about other concepts that they may don't know yet, and that's very frustrating to them sometimes. And of course, for non-technical education, imagine in a medicine school, you need to interact with signals or with currents and different tissues. You are not an electrical engineer, and maybe you don't know some concepts, but you can have an application and a very simple device. You connect it to computer, and the designer, the teacher, whatever, he or she has designed an application, and he or she has translated everything to you. So you are seeing medical concepts, medical parameters, or parameters that you can understand, and you change them, and the application can translate everything into the electrical concepts and then the final parameters, and then reconfigure the FPAA. So you have like very important applications here for different scenarios. What we did is we created different practices using this dynamic reconfiguration for higher education, but in order to show the potential of those things that I have said just now. So we developed 5 practices, one for the introduction and 4 real lab practice, and we use the algorithmic method because we think that's the most powerful in this environment. So just to talk about an example, what we did here is we use a light sensor, because we only need the light sensor and the FPAA. So this is very, very simple. And what we want to do is we want to convert the current, the input current from the sensor from 2.5 to minus 2.5 voltage limits. and then we will compare with another signal, and we will offer an output so we can control, for example, a diode. When the light is off, we want to light the diode on, and when we have a lot of light in the environment, we want the diode to be off, for example. So this is the final design. It is not that hard to build, very easy to understand. We can check, for example, what resources we are using from each cap. So it is useful to know if we can build more complex things or not. And the goals here were those, and I think that is important, and I bet you will find some of them very interesting. First of all, to know the different camps, that's obvious, but the second one is not obvious. For example, to observe the limitation of the FPAA. This is one specific thing for this FPAA, but I think it's a very important concept for engineering students. For in this case, the FPAA has 4 volts limit, internal limitation. So we are not going to be able to work with more than 4 volts. And we are going to see why this is important now. This would be like the final application, but in order to move the current to voltage and to a certain limits, we need to transform this signal. So if we measure, for example, when we are in complete dark, we are going to get 0.3 volts, and when we are in complete light, we are going to have 3.1 volts. We need to transform those volts, 3.1 and 0.3, to 2.5 and minus 2.5. It is so easy. This is the equations, but if we solve them and we get those values, they are in theory completely valid. But let's see what happens when we are in the complete light scenario. We have 3.1 volts, and we are going to multiply that by 1.7857. We are going to get more volts. So we are not going to get any error, but we are not going to get the correct result. Our application is not going to work as we expect. So we need to change the way we are thinking here, and we need to design this in another way. So this is an important concept in higher education, because not always the straight solution is the correct one, and sometimes it's not worth it to change the internal limitation because there is another way to do it in a more efficient way. Well, once I said that, I think it is important to see here in the application interface everything. We have, for example, I'm sorry, because again, it is in Spanish, but we have the limits, 2.5 and minus 2.5. We can change them. We can change also the values when we are in the scenario of high light or completely dark, because our light sensor is going to be different. So in the real world, if a different student use another light sensor, he's going to measure anything, and he's going to say, okay, mine is not in completely light, it's not giving me 3.1, he's giving me 2.9. Okay, you can change that. You are going to get also the correct result. But the important thing here is if you can see the Y value and the X value, we can show the student those values. So if they have been working with the equations, they are going to be familiarized with them. And we can translate those physical concepts into the theory concepts. And we are going to be able to show them, okay, if you change that, if you change the high light voltage, everything is going to be affected that way. Okay, and we can translate that to internal components value. For example, the gain here is going 1.79. We're going to have that, or we're going to have the offset value too. So that is very important for engineering students to understand what they are doing. We have this, they are going to be able to play with everything, to change the parameters, and since it's so quickly and easy, they can do it a lot of times. Normally, in a normal lab with discrete components, you can do 2-3 different practices, because you need to change everything, and sometimes mistakes happen, and then you need to reveal it, and you don't have enough time to perform a lot of different iterations. The application is well intended to serve as a guide. You can include instructions, you can include explanations. So it is so easy to transform this application into an application for a mid-school practice forever, for example, or for a medicine school. So you translate everything, and the student is the only requirement the student needs to know is the concepts they already have seen in class. So no, it's difficult to do that. And I think I've been spoken for too much, but the last thing here is for remote laboratories. Once we have the FPAA, we know how to program them, we know how to reconfigure them on the fly. We have endless possibilities to do a lot of things, but in remote laboratories case, we have like 3 main ones. The first one as a dynamic component. I bet a lot of you know VSIR, and when you use VSIR, you have the component and you put it in the breadboard, and then you check the final results, and that is like magic, because you are really using a physical lab from your home. But now imagine you have another component, for example, a filter. You can enter the corner frequency. You don't need to pick just one, or you don't need to build one with discrete component. You can say, okay, I want to use a filter. I want to use a multiplier. I want to use a gain with this parameter. Then the same control unit that control VSIR can control the FPAA, and the FPAA in this case will work as a filter, or will work as a multiplier, or will work as a signal generator, and we can create the lookup table. So that's powerful. We will have like a very versatile component, and we can configure it on the fly. So also as a helping component. Sometimes we need to build, we want to be our remote laboratory more versatile, and we want to adapt some signals, some measures, and so on. The FPAA is the perfect component to do that, because with just one component, you can adapt different signals. You can measure. You can have to measure the signal in different ways. You can change its function the fly. So it's so easy. And as a lab, if you just have the FPAA, you can connect remotely. You can have different applications, or you can have the Analytic Designer. But I think that the most smart thing to do is to have different applications. You can load the primary configuration, lab 1, lab 2, lab 3, and then you can interact with that with the parameters you let the students use. So this is going to be always safe to use, because you just let the student what you want them to use. You are going to expose them just to the concepts that you want them to be exposed, and you can let them focus on what is really important without the risk of losing time with other concepts that they may don't know, or they don't have to know at all. And that is all. Thank you for your time. Now I will answer your question, if any. And since I have a very uncommon surname, you can find me easily on LinkedIn, Google, and this is my email. If you want to write to me asking something or whatever, I will be more than happy to answer to you.
Thank you very much, Alex. Thank you, James. Then we will start the rounding for questions. You can do questions, putting them in the chat, or putting them in the questions and answers, or finally, you can stand up the hand you have in any one of your names in the web thing, and then you mute your micro and you can do it. I believe that you have new ideas now about the applications and teaching FPAAs. One question they have in mind is that how is now your PhD? How are evolving this, and when do you expect to have this more ready to start to share in the lab and so on? Well, I don't know nothing about.
Yeah, that's pretty question because Manuel is just my thesis director, so he knows everything. But we expect to finish it this summer, more or less. We are now trying to create the real application with Visir, and also in the standalone laboratories, we already have those practices. The one in SOU is working. We have 5 more with temperature sensors, with different applications. So that's the state. We have published some articles, papers. I think they have been quite interesting, but yeah, that's the state, and that's what we hope.
And one more question, mainly regarding for the people that is attending. The integration between Visir and the FPAA should be, I believe, is a win-to-win integration, because normally the FPAA is really good when you change the environment and you change all the components there and so on. And this is one of the things that Visir, as a high-speed multiplexer, can do it really fast, really easy there. Do you think this kind of connection would be really good to have in the future? Some self-reconfigurable or self-changing parameters in a hardware parameters around the FPAA should be feasible for future applications?
Yeah, sure. I think that's what is one of the main applications for remote laboratories. I mean, you can use the FPAA as a dynamic module, so it will be like another part of VC, but of course the FPAA is going to benefit from VC because you're going to be able to use all its components to interconnect with the FPAA, and you can create different external environments, different sensors, and so on. And the most important thing, they are real. They are from a real physical lab, and you are not simulating anything. You are just building it on reality.
Yeah.
Some more questions there?
Yeah, Alessandro, it was a very good talk. I think most of us, we were not knowing much about FPAAs. Now we have inspired us to set up this lab. So really, it was very interesting. Let us. I think now I feel like having something hands-on on FPAA and try out. We are comfortable with FPGAs, but not FPAAs. It was really a wonderful talk. There are some of my first-year students also here. Sri Raghav, I think he has a question. Sri Raghav. I think one of the attendees.
I think the question is, what is the difference between FPAA and FPEA?
Okay.
Furthermore than the G and the A.
Yeah.
For Professor Manuel, one small, there is one subsection chair, Suresh Jangam Shetty. Please make him a panelist so that he will speak for 2 minutes.
Whom?
Suresh Jangam Shetty. Suresh.
Yes.
Yeah. He is
okay.
there. Yeah, he is the subsection chair of the IEEE Bangalore section. He is the senior most IEEE Education Society member. I think Suresh Jangam Shetty, sir.
Yeah. Thank you.
You can.
Thank you, Professor.
Yeah.
Portugal groups. 5 days of this program meeting to attend, and I've gone through all the deliberations. It is really impressive. Thanks to pandemic that we all are meeting online. That's the whole world is made into a small network that we are able to see each other. I'm very much impressed with this remote laboratories that initiation this UNED has taken. I really appreciate all the 5 speakers and the 5 topics selected for this particular presentation was very good. I'm sure I am also very much keen to initiate a lab in this regard in our institute. 500, 400 miles away from Suvaredi, north of Bangalore to north of Bangalore, around 500 kilometers, we can see. So I'm so happy. Definitely continue to interest. And my association has been 33 years with IEEE. I'm in the power and energy system, and last 10 years with IEEE Education Society. Though I have gone into the main office bearers or positions in IEEE, but on the chat, I always feel I should be. I have been reading a lot of articles from IEEE Transaction on Education. It's very good. We came to the IoT, then trying to conduct experiment. The second talk impressed me very much because here in Bangalore, working with IoT with a solar box cooker. I have connected here the data and how much time it is going to take for cooking. And we have developed an app also to help the user in rural India, that in mobile only they'll come to know when the food is cooked in the solar box cooker. That was the first application we have initiated here in Bagalkot. So now when I went through all the 5 days lecture, we can very well now convert that into a remote experiment for the students. This has given me a new idea. Thanks to all the speakers, very senior people have worked. Sergio Martin, then Leo, then Pedro, Alessandro, and today's speaker was Alessandro, and I was very much impressed. So, Manuel, I should really personally thank you for initiating this whole event, bringing almost two continents together on one network. Thanks a lot. Thank you, Shivareddy sir, and to all the speakers.
Thank you.
Thank you. And Alex, do you have some possible answer in general about the things there? Thank you very much, Train. And we have one more question from Iswanata about that. What should be, of course, the difference between FPAAs and FPGAs, but this is easy. But the other one is in which applications the FPAE are a weapon over FPGA. I believe the difference is that they are not compatible because they are different words. They can share some part of the words there, but it's difficult to have this in the same one. But what should be the more powerful or the more concrete application that should be really good applied by the FPAA?
Yeah, sure. I think those two questions at the same time because they are very related. The main difference is the FPGA is going to work in like the digital most of the time. The FPGA works in the analog world. So if we need to work with signals, the good option here is the FPAA. If we need to move a signal in order to measure it in another device in a more efficient way, the FPAA is an option. If we are going to do some digital processing, FPGA is the option. So, for example, in application, I think you are going to see the difference very easily. If you are using, imagine a neural network, in a physical neural network, we are just using digital parameters. The FPGA can perform that task. But imagine we have a neural network but for analog signals, or for example, in a control environment, we are using a PID as we saw in the presentation. The FPAA is a better option here because we can work in a native way in that analog world. We don't need converters. We can work in quicker, and we are going to be able to adapt the FPAA itself in the same amount of time that the FPGA is on chance. Because in general, the analog devices, one of the main constraints is that once you build something, you have built something. You cannot change that. But with the FPAA, you can change that on the fly as a digital device. So I think that's the main difference. I would use FPGA for digital application, and I would use FPAA when analog signals, measurements, sensors are involved. And of course, they are a very important concept too. I think it's STMA, which is a mix between FPGAs and FPAA. And that is important because you can use both of them as a whole, and that's a very important concept too. So you don't need to use one or another. You can use two of them and get the best of both worlds, analog and digital.
Thank you very much there. I don't know if there is some more questions to finish in this nice session. One of the things, for example, in the every day there is much more working in the digital world, but some things are working yet in the analog world. And in these activities and this area, for example, in some part of the autonomous machines, and some part of things that when you are using a lot of analog signals and you like to make decisions over the analog, not in the digital, the FPAA should be some applications there in those cases there. Okay, I believe there are not more questions today. This is Friday. It was a really long week. Thank you very much for all the people. We finally have 434 people registered for the different sessions. We have the maximum of the attendees people was in the first day. So we had 100 people attending the first day, and on the other 4 days we had from 90 to 70 people attending. Today we have in total in the biggest place today we have around 58, 60 people attending today. Thank you very much for all the people. Thank you very much for the attendees. Thank you very much, Siva. Thank you very much, Suresh.
I think I would like to thank Professor Manuel Castro, who was instrumental in coming up with this webinar series. On behalf of IEEE Education Chapter, Bangalore section, IEEE Bangalore section, we wholeheartedly thank you, sir, and we hope to continue this networking on the IEEE platform for the betterment of the higher education, for the betterment of the society, and keeping in the vision and mission of the IEEE intact. I have my subsection, one of the subsection chairs, Suresh Jangamshetty here, Dr. Bindu Thomas, my IEEE Education Society Bangalore chapter secretary, Dr. Bharti, and I would like to thank the Portugal IEEE Education Society president is here, and all the panelists for the last 5 days who made this particular webinar series a very useful one. And probably I feel in a year we will meet twice to have some of the series like this. If Professor Manuel Castro gives green signal, in a year at least twice we should meet, so that we will have an opportunity to meet the people on the other continents. Meeting physically would be very difficult, keeping the economic issues, but there should not be any barriers to speak like this using WebEx when technology is at its peakest for communication. I think we should make use of this for the betterment of the society. Thank you so much, Professor Manuel Castro. Let us try to do good things in the best possible way. So what else I can tell?
Thank you, Siva. Yeah. And thank you to all the people that attended those days, all of our colleagues, like the current president of the IEEE Education Society, Edmundo Tovar, the president-elect, Martin Llamas, the past president, Russ Meyer from Milwaukee, and of course the director of the Region 9, Teofilo Ramon, that is attending today too. Thank you very much to all our good colleagues, good friends. Thank you from Spain. Have a good time in India, in the United States, in any place in Portugal, any place you are there. And take care, be really careful, and we will be in the next month, for sure, we will have some other activities together in the synergy, and we will have some things to work there. Thank you very much.
Thank you so much. Thank you so much.
Thank you. Thank you.
Bye.